Mkwaje majama, look who's back here, like I never left. Yeah, hapa YouTube, consistency is the key. So this one was sent to me by a viewer on TikTok. It's an Oraimo adapter here. Let's see what's wrong with it and see if we can fix it. The first thing that I always do is confirm here if it's working. So I'm going to plug in it into the mains. Yeah, and this is a USB meter, so it measures the output and also can measure current that is going out from an adapter. And you can see we are not getting any reading from the USB A port. Also same for the USB-C. Nothing. And the other USB-C port also no reading, no voltage, I mean. So I take my meter, I switch it to resistance. Yeah, don't worry. Let me place the meter on the screen so that you can be able to see. Perfect. So take your meter, check the AC connectors. Yeah, you should be able to get a reading if the connection is okay. Yeah, if the fuse, the NTC, the filters, they are fine, you should be able to see a certain reading. And you can see on this one, we are not getting any measurements at all. If I compare it to another good one, check on the screen. Yeah, 5.7. So there exists some form of resistance in this one. So this resistance is, you can think of it as the resistance of silicon. Yeah, you should be able to see the PN junction maybe of a diode, of a switching transistor, or a capacitor, you know, charging or resistance changing. You should be able to see something, but this one giving me zero, no reading at all. It tells me most probably a fuse or a connection is broken between the AC terminals and the board itself. Next thing to do is to take this thing apart. So these things, they are not meant to repair, right? So you have to find a way to go in. I tried to pry it just a little bit to see what's going on, but I can see there's this seam that is going around on this area. So it seems like, oh, this is a cover. Yeah, so this one pulls out, and this piece and this other piece remain intact. Something bad happened. Yeah, that area is black. It's something like blew up or something. I want to see if we can take this shield out, but it's soldered here and here. And also we have a bottom shield here, and this one is coming out very easily. So we need to get it off from this soldered joint, and the board is looking pretty nice, I can't lie. And the shields are out. So let's first check the voltage on that capacitor, which is this big one. So it has like 2 volts, so that's fine. Then I'll try to remove all these resin and thermal pad if it's possible. Some of it is very stubborn, as you saw in my last video. I can quickly do a small rundown of what we are seeing right now. So you have the AC inputs here. There's a fuse, there's a class X cap, there's a this one common mode inductor. Yeah, sorry, you can't see. Then you have the bridge rectifier, 4 diodes in this package. Then the output of the bridge goes to, what is this here? This one, because it's written here CY1. Yeah, CY1, this is it's a safety capacitor. Yeah, it's connected between the output and the input. Then from the bridge rectifier, you can see this track goes to these 2 points. Yeah, and these are the capacitors. This one, the high voltage DC smoothing capacitors, and the other one, which is this one. So these two, they're in parallel. From the positive of the capacitor, it goes to this point. What is here? It's another capacitor. Here. Is it a capacitor? I think so. Yeah, it goes to the capacitor. Then from the capacitor, goes to this chip. We don't know what it is. This is a gallium nitride charger. So this probably is the high frequency gallium transistor. Yeah, instead of using a normal silicon transistor, these chargers, they use gallium nitride. Then you have a bunch of resistors here, probably the current sense shunts here. And this gallium nitride is driving the primary of this ferrite core. So this is a switching power supply. It's a flyback. And you have a chip here. This probably the PWM chip. This is what is driving this gallium nitride transistor. Yeah, you can see an optocoupler here. This is what is connecting the primary and secondary. Yeah, so depending on how the optocoupler behaves, this PWM IC can be able to increase or reduce the duty cycle, and can be able to vary the voltage on the output, right? So on the secondary, now we are done with the primary. This is the secondary. The secondary, we have this IC here. I think I talked about this IC last time, which is the synchronous rectifier. Instead of them using a diode, they are using a transistor, probably an N-channel transistor. So this one has almost no voltage drop when it's on. So very less or no power at all is dissipated by the rectifier. Do you see these caps here? Yeah, these are sitting on the secondary output from the transformer. So after rectification by this synchronous rectifier, we have the voltage appearing on these caps here. Now on the ports, you can see we have like an inductor here. This inductor is a buck converter, right? So what happens is, when this voltage appears on the secondary rail, let's say something like 20 volts, this buck converter is stepping down that 20 volts maybe to 5 to 12 to 9 volts. The default voltage from each port is 5 volts. When you connect your charger, it communicates with your phone. Your phone can be able to request even 9 volts. So what happens is, if we have 20 volts on the secondary rail, yeah, the buck converter steps it down to 9 volts, which is using this coil. And probably we maybe see a diode or a MOSFET somewhere. I'm not sure if you can see, but in here we have packages like that look like transistors. This transistor is driving this coil here to reduce the voltage. This is another coil. You can see almost the same shape as this one. So probably this has two buck converters, so that the port can operate independently of each other. So one port can be supplying 9 volts and the other port can be doing like 12 volts. These caps, they sit now on the output of the ports. And that's it. We can try and check what's wrong with it. Yeah, we can do a few tests with the multimeter to check if our fuse is okay, our bridge is fine, is the output shorted, is the gallium nitride transistor okay. Yeah, We'll start here from the AC inputs. We already know maybe the fuse is broken. So let's check the AC inputs. We don't have any shorts. Yeah, you can see 0 on the meter. The fuse is also open circuit. So we have no reading on the fuse. Like 6 mega ohms. 40, 50. The fuse should have like 0 ohms. Yeah. Then what are we checking? We are checking the parallel of this class X cap. So we don't have any short on the class X capacitor, like 100 kilo ohm. Then all these resistors you're seeing here, these are bleeding the class X capacitor. Here we have the input of the bridge. So from here to here, the input of the bridge also has very high resistance, like 800, and it's going up. The output of the bridge is also not shorted. Yeah, you can see we have very high resistance, like 15k, 15 kilo ohms. What about the bridge rectifier? I'm going to switch to diode mode. So on the bridge rectifier, what I'm checking for is the voltage drop of 2 diodes. Yeah, the bridge has 4 diodes, but first what you want to check is the 2 diodes that come from the AC input to the DC output of the bridge rectifier. So when you place one probe on one AC input, you should get the voltage drop of one diode across the output. So on this output, we have 0.4. On this output, nothing, right? Switch to the other AC input. On the DC output, 0.4. On this other probe, nothing. Here you can see. So the diode is coming from this AC input to here, and from this AC input also to here. So this point here forms the positive of the DC rail, or the high voltage positive goes here. The same case, switch your probes. Now put the positive to the output of the bridge rectifier, right? So on one, you should be able to see 0.5. Here we have nothing. Here we have nothing. Here. So you can see we have no diode going from the positive to the AC inputs. But if you check on the negative, the negative DC output of the bridge, you should be able to see 2 diodes on the 2 ends of the AC input. So from here to here, 0.4, also here to here, 0.4. So this bridge is okay. Let me switch to resistance on the meter, and we are measuring in the kilo ohm. Yeah, like 15 kilo ohms. On the other capacitor, we should also have very high resistance, like 50, 57. Why 57? But we measured on the output of this, like 16. Why is this capacitor? Why does it have very high resistance? This one is in the mega ohms. Okay. What about this one? Oh, these two, they're in parallel, so the same reading. Then what is the miss between the output of the bridge from this capacitor to this one? Oh yeah, I can see what went wrong here. Look at that capacitor. Let me try and focus for you guys. Yeah, this capacitor has a big bulge on it. You can see. I don't know if you can see it, but if you compare to these other caps, you can see how these other caps, they are very flat on the top, but this one has a big bulge on it. And I also don't know what is this blackened area here. Do you think it started to leak? Yeah, this capacitor is what failed on this adapter. So maybe it was failing, it started to draw a lot of current, and the fuse blown. Then this could be a very easy fix then. So we'll just try and replace that capacitor. So I'm going to tin these parts with low melt solder so that you can be able to pull that capacitor from the other end. If you're wondering, yeah, that capacitor has a big hole on it. And look, all that blackened area, it's where that capacitor had exploded before. So this is the electrolytic that had vaporized from the capacitor when it exploded. And my capacitor is out. 400 volts, 33 farads, microfarads, sorry. So not a very high capacity. So let me see if I got something similar that you can fit. What I have right now is 10 farads, 400 volts. I'm sure it's going to work fine. Right now, we are just doing this for testing. Now let's rebuild that fuse with a jumper wire, of course. Perfect. Now is ready to test. And of course, when you are testing all your power supplies, you should make sure you're using a series bulb. Okay? Fantastic. Power on. No explosions. And do you have any voltage? And what? It's still not working. Do you have any voltage here? No voltage on that capacitor. No, we have something. We have 310 here. What about the output caps? You're not getting anything. I mean, we should be getting something on the output even if we are not charging any device. Yeah, maybe something still is wrong on the primary area. And we are back on the scope and I found something here. Do you see here? Here we should have a capacitor. Yeah, you can see above it we have this R16, which is this resistor, below it this C6, and we are missing a capacitor here. Yeah, I don't know what happened. Did it just fall out, or is it because of my unconventional means of opening it? So that capacitor looks like something important. You can see it's connected on the gate of this carrier transistor. Yeah, maybe it's something to do with reducing oscillations or decoupling, filtering or smoothing the signal to drive this transistor. So maybe it's kind of important. I don't know the value of this capacitor, right? So it would be a very terrible idea just to fit any capacitor here. I could not find any data sheet about this transistor and where it's applicable and any associated circuitry for this transistor. So I'm just thinking of putting a very, maybe like 100, you know, nanofarad capacitor here and see what happens. Before that, let's check a few things. Diode mode. We have a bunch of capacitors around that area, and also we have diodes. We're getting 0.7. What about the other way? The other way, the diode is not conducting, so it's fine. We have another diode here. It's conducting on this way. So it's conducting both ways. That's not a big deal. Maybe something on the circuit it's skewing the reading. So we have another diode here. 0.5. This is not conducting the other way, so it's fine. What else? We have another big diode here for the snubber. 0.5, and it should not conduct this other way. This other way it's okay. And you have these resistors and capacitors. So these resistors for 47 ohms, two in parallel, so maybe like 25 ohms total. So this one they are smoothing the reverse voltage recovery for this diode, and this other resistor in parallel with this capacitor is the snubber. So this one is what is dissipating, the back EMF from the primary winding when the transistor is off. And this is the primary winding, has very low DC resistance, and this is the secondary, also very low DC resistance. The switching transistor is here between gate and source. Nothing. The other way around, we have a 0.8 drop. Maybe it's okay. We have current sense resistors. These are very low resistance, so these are fine. And this is the positive and negative of the high voltage capacitor, which is okay again. So I'm not seeing a big issue here. Let's fit a capacitor in here and see what happens. You know what? These resistors here, they're looking kind of sus. Like, I can see this one, like one end is falling apart. So this is like 2.2. You can see 2R2. So this is 2.2 ohms. I'm going to replace this resistor. What about this one? This one, the markings, they are fading. So we kind of have a hard time here. But I can see the first letter like a 6. Yeah. And you can see on the meter, we are measuring something 6 point something. So I'll just take what the meter is reading, 6.1 kilo ohms. I really can't find any of these two resistors, this 2.2 and this 6K. I mean, they look like they are falling apart, but they are still working. What I really want to do is find a capacitor here. And I don't know the voltage, I don't know the capacity, but this gate here probably needs something like, I don't know, 20, maybe 15 volts. Yeah, maybe I can use 100 nano farad here and a 50 volts capacitor. This is what I have here, and they're too big. This is too big. What I can probably do, because this track goes here, yeah, you can see, so I can solder this end here and maybe this other end here and not use this pad anymore. I mean, everything is looking good. From here to here we have 500 ohms. Yeah, that's present. Our 2.2 ohms is still okay. Yeah, then our 6 kilo ohm, perfect. And this point and this point, they're not shorted. Yeah, we have like 6 kilo ohm. So I think now we proceed and test. Very nice. No explosions. But is it working? Look, it's working, 5 volts. Does it charge? So this is my tablet and it's charging. Yeah, you can see. So the adapter is working just fine. I'm not going to test all the ports. Our issue was not on the output, but on the input. We fixed it. Yeah, this is a nice adapter. It has all the PD charging, the Qualcomm, yeah. And it's a shame because normally this will be disposed in a landfill somewhere for such a small fix that everybody can do. Now it's all about replacing that capacitor with the right one, like 30 microfarads, then finding the right fuse and remove that jumper wire, and also do a few tests, when the power supply is loaded, and check the waveform of the transformer if there's any ringing or distortion caused by that ceramic capacitor that we fixed on the gate of that transistor. But other than that, the adapter is working. I don't see any big issue with it. I hope you enjoyed this video. You learned a lot about a power supply, what to check, how it works, and like and subscribe, and I'll see you again soon. Bye.